I would like to pass the time to Professor. Please, thank you very much.
Thanks a lot. Thanks for the nice introduction. And hopefully I can present you some interesting things here. So it's quite demanding for me because I don't know what really is your expertise on it. And what I love to do is always is um, to to give an to give an idea, like a technical introduction that then later turns into a more social science discussion about what is really deep learning. Can you see the presentation? Is this fine?
Yeah, thank you very much. Yes.
Great. So um, as I said, I don't know what your expertise level on this is. So perhaps there will be some questions in the end, and I'm very happy to go into a discussion with you on this. But we all know that artificial intelligence is becoming more and more important, and there is a kind of artificial intelligence revolution going on. And the first thing we should think about is what is artificial intelligence, and if we start thinking about this, I think it's quite important to realize that we have the whole field of artificial intelligence that has been around since probably the 1920s. If you think about Turing and the Turing test and the idea of inventing computers that are somehow intelligent. But this whole field is, there are several subfields in it. And one subfield of artificial intelligence is what we know as machine learning. And we will focus on this more. And especially within the field of machine learning, we have this special class of algorithms called deep learning. And when we are hearing anything about the marvelous things that AI is doing today, we normally now talk about deep learning. And this might be quite confusing. So if we are talking about autonomous driving, it's deep learning. If we are talking about um, image recognition, videos, computer vision stuff, identifying people in videos, or facial recognition. This is deep learning. Or if you are talking about the latest developments in natural language processing, NLP or NLU, natural language understanding, we see that there are now computer programs that are able to generate new text like GPT-3, and this again is deep learning. And the same is true for all the advancements in from AlphaGo to AlphaZero, uh, all the advancements in robotics. All this seems to be really focused on deep learning right now. So it makes a lot of sense, even from a political perspective, to go a little deeper into this concept of deep learning and understand what is really going on there. But before we do this, we should keep in mind that there is a second field of artificial intelligence, traditionally called artificial general intelligence or strong AI. So this is the idea of really creating computers that are as intelligent as humans, whatever intelligence means. We don't know what intelligence is, but most researchers in the field of AI still are very confident that at a certain point we will reach a level where computers really start to think in some way. But the problem is, from a scientific perspective, we don't even know if this field of artificial general intelligence is connected to what we know as AI at all, or if it might be a totally different field without any connection. But the political debate about artificial intelligence, especially when it goes to the public discourse, is often framed by the ideas of artificial general intelligence, the Terminator scenario. So we have to be careful with artificial intelligence because then Skynet takes over and we all gonna die, or things like this. So as you will see in the next slides, there is probably nothing to worry about deep learning, that it will turn into a Skynet Terminator thing, or transforming the whole world, the whole planet into into a machine that is creating paper clips, which is another ethical AI scenario. So why is it this so? What is the difference? If we talk first about machine learning, there is very famous definition what machine learning is by Tom Mitchell. And Mitchell said a computer program is said to learn from experience E with respect to some class of task T and performance measure P, its performance at task in T as measured by P improves when with experience E. So the idea behind this is, and this is very important, when we talk about machine learning, we have a predefined task. It's not like we are creating any intelligent machines in the way like we would normally understand intelligence, but we have a very, very defined task, and only in this task the machine learns. And learning really just means that it takes some information out of experience, which is normally connected with data. So the computer is learning something, and learning is already defined in a way that it leads to a better performance, and we have a distinctive measurement of the performance. All this is given even before the computer program is running. And Andrew Ng, which is he's one of the big rock stars in artificial intelligence. You probably know him. He turned Baidu into a real AI company, and he has said almost all of AI's recent progress is through one type, in which some input data A is used to quickly generate some simple response B. And this is a very simple definition, but it's a very good definition of what is really going on in artificial intelligence. This is what we call supervised learning. So the idea is we have already a data set where we have some input and we have an already known output. And now we fit a mathematical function that our input is produces an output that is close to what we already know would be the result. So if we look at these parts of machine learning, then machine learning is always about three different mathematical concepts. We have a general model at the beginning. So this is a mathematical function where you can insert the input, and input is quite vague here. It's unstructured data, but to work, for example, with words, you have to transfer words to numbers because computers work with numbers. So you will have some way to create numbers as an input data. Then you have a mathematical function, and this mathematical function produces an output. So the mathematical function is exactly what we saw in the definition by Mitch, that this is the defined task. The task is already completely defined in the mathematical function that we use. Then we have our cost function, or sometimes it's called a loss function, and this is the performance measure. So we have already a mathematical concept how to measure if the model works good or bad or better, and what learning is. All this is given upfront. And then we have an optimization algorithm that is used to optimize the parameters in our model is getting now. And if we now turn to neural networks, because deep learning is based on neural networks, there is a lot of hype around neural networks. Like it's a neural network, it works like the brain. This is totally bullshit. A neural network has nothing to do with the brain. It's just another way of representing a mathematical equation. In this example, we have two inputs, X and Y, and let's say the inputs could be 0 or 1. And then we have what we call a neuron that is just, in this case, summing up the inputs. And if the sum of the two inputs is 1 or bigger, then this neuron will send a signal. This is what we call a perceptron. And in this case, so if the neuron is looking for a value 1 or higher, then what you see here is the same as a logical OR. It's an OR getter. So if X or Y is 1, then the result will be 1, and there is a signal that is given. And now we can make this a little bit more general. So if we expect different kinds of numbers and not just 0 and 1, and we add this W1, W2 here, these are weights. So this means we take our two inputs, let's call it x1 and x2. We multiply the input with a weight, with a parameter that we don't know yet, and then put this combined input into a function, into an activation function. This could be a sigmoid function, so that depending on the multiplied input of our two neurons at the beginning, we get a value between 0 and 1. This is something that is done very often. And if we take this perceptron now and combine it to a network, then we have already a fully working neural network. We have our two inputs. We send the signal of the input to, in this case, 3 different neurons. In these neurons, the input is multiplied with weight and somehow transferred in an activation function. And all the results from the 3 neurons are then again transferred in another neuron, so that we get our output y hat. And now we can compare y hat with what we have already in the data as the output that we would like to achieve. So you see at the end, there is our cost function. This is where we can measure how good the performance is. We have the activation functions in the neuron, and we have a lot of weights already in this very simple network. And this is, all the weights are what we call in machine learning trainable parameters. So these weights have to optimize in a way that our y hat value gets closest to our y value that we already know from the training data. And how is this done? The basic idea to do this came out of political science, by the way. So there's a very strong connection historically between political science and artificial intelligence. So one of the, let's say, godfathers of artificial intelligence is Herbert Simon. He was a political scientist, and he was working on neural networks in the 1950s already. And the basic algorithm to optimize all the weights that we saw, this algorithm is called backpropagation, and it was developed by another political scientist, Paul Wurbis. Paul Wurbis is not well known as a political scientist now, because he was so successful in inventing this computer science methods. But nevertheless, he was a political scientist, and this was part of his dissertation. So he had an idea. The problem was, how do we find the right parameters in the neural network? And his idea was, we just start with random numbers. We just take any kind of numbers for these parameters, and then we can calculate the network one time, so that we get our y hat, we get our value that we can compare to our to the value we would expect from the network. And then starts backpropagation, which means you take the differential equation of the cost function, and then you can see how you should alter, in which direction you should alter the weights to get a result that is closer to the result that you want. And you do this with all the layers in the network. So you go back to the beginning, and every time you alter the weights that you at the beginning had randomly set, a tiny little bit, which is called the learning rate. Now you have new weights, so you can calculate a new y hat value and compare this again to the already known output, and go back and forth and do this billions of times. And then you will find a very good setting for the parameters you're looking for. And there is some more stuff about this. So this is the basic algorithm. Today we do it more, it's called stochastic gradient descent. So we are not training the model on all the data, but always take a sample of the data called a batch. And this leads to a situation where we prevent going into local minimas. But in the end, it's still the backpropagation algorithm of Wurbis. So what is now the difference between neural networks and deep learning? On a mathematical level, first, there is no difference. Deep learning is just a neural network. So it's just this um, representation uh, of equations. But deep learning is a little bit more, because it's not just that you have a lot of layers in the network, a lot of neurons in the network, but you also alter the structure of the network. And what we see here is one of the first real deep learning algorithms. It's called long short-term memory network, and it was invented by Hochreiter and Schmidhuber at the Technical University in Munich in the 1990s. And without going into details, but the main idea here is that instead of just connecting each layer with the following layer, you have feedback loops now. So a signal that is created in one point in the network will go back to the input of the network again. These feedback loops help you a lot to understand sequels in the data, because now suddenly the result is altered. If you let's take words, for example. If you enter a sentence in a classical machine learning algorithm, if you work with any kind of words, what would happen is what we call a back of words approach. So the machine learning algorithm finds patterns based on the frequency of words in the text. But as you all know, there is more to a text than just the frequency of words. So the order of the words is very important. And this is something you can get with a long short-term memory network, because of the feedback loops. Now each word might have a different meaning for finding a pattern, depending on what is the preceding word or the following word. And actual deep learning algorithms even go one step further. So, for example, the BERT algorithm, this was invented by Google and is now used in the Google search engine. There, the idea is that we want to find a way not only to look for the frequency of words or the order of words, but also for the position of words in a text. And this is done again simply with neural networks, but the idea is that we have two separated neural networks trained, and then we form a kind of correlation matrix of this separated neural networks. And by the correlation of the weights, we then see which position is more important in general than another position. And this improves the performance a lot. What these real deep learning networks now can do, like BERT and Alberta, and they all got fancy names. Or then GPT-3 is a big thing now, the OpenAI model in natural language processing. These algorithms today really outperform humans in many tasks, like natural language understanding. So a task where you read a text and then you have to answer questions about the text. And this is something where computers today are outperforming already humans, and we are just at the beginning of this. But the problem in which we run there is that these models are getting bigger and bigger and bigger. GPT-3 now has really trillions of trainable parameters, and it's very very costly to train this model, and it's nearly impossible to understand what the model is really doing in the end. And this leads us to the problems with deep learning, first from a technical perspective and the handling in the community. So interestingly enough, there is a big theoretical problem. Many things we know in deep learning are not proven. It's a whole mathematical concept, but there are no proofs for many of the problems we are facing. So there is no mathematical proof why a ReLU function might be better than a softmax function or whatever. So it's even not theoretically not really clear why these deep learning networks converge to an optimum at all. It's really crazy. But the handling in the community is just, if it works, it works. So if you can build a model and you can show that you have a better performance with your model on any kind of standard data set, then this counts as scientific progress, which is very frightening because we still don't know why the performance is better. So this, if it works, it works mentality is a big issue for what is going on in the technical development right now. Second problem is all these calculations, these billions of calculations are computational very intense. And the handling is, we use parallelization. So that deep learning is such a thing has to do a lot with the hardware development in computer games, because the GPUs, the graphical processing units that you have in modern computers for playing nice computer games, they are able to do basic calculations in parallel, like thousands of calculations at the same time. And this is exactly what is happening in neural networks. So you have very basic operations, like just multiplying some numbers, summing them up, very, very basic, but you have to do trillions of operations. So parallelization with GPUs is the way to solve this problem of computational intensity. But the faster the computers get, the bigger the models get. So we are still at a point where a state-of-the-art model needs like weeks of training time on the best computers in the world. Another problem is overfitting. Overfitting means you will many times come into a situation where your model works perfectly on the training data, but if you want to apply it in a new setting, it doesn't work at all. But there are many tricks in the deep learning community how to prevent this, like penalization, dropout, cross-validation, whatever. If you are looking at the applications of deep learning today, there is a huge difference between what is really the state of the art and what is taught at the universities, our university, or what is developed by Google and Facebook and Baidu, and the things that are really on the market now. Mostly everything that is called artificial intelligence or deep learning in normal application is really bad from a scientific point of view. Okay, beside these technical problems, we have some issues that are very relevant for political advisory as well. So first of all, we have the point that these models always find a correlation, but they don't find causality. The effects are undirected. And neural networks are very prone to find the so-called inverse function. For example, if you have an algorithm that is detecting what is on a picture and you show a photo of a dog, then the algorithm says, oh, this is a dog. You show a photo of a goat, this is a goat. But if you show a photo of someone holding a sheep on his arm, the algorithm will probably say this is a dog. And then you realize, okay, the algorithm does not understand what a dog is or what a sheep is, but it's just getting some signal, some other signal out of the background of the picture, for example. There was a paper some years ago where scientists claimed, scientists from China, they claimed they could use deep learning to predict from a picture if someone is a criminal or not. And the model worked very, very fine on the training data they had. But the problem was the picture of they took was police pictures of criminals, and then pictures that were made in big companies for the ID cards of the employees. And on these ID cards, everyone was dressed nice and had a white color, and stuff like this. So in the end, the algorithm did not, of course not, because you cannot see it in the face of anyone, did not find a signal to say someone is a criminal, but it was just looking for white colors, and this was more or less all it was doing. So a second critical point is, and there is a lot of true about this, is that um, uh, deep learning is always based on routines. It's conservative. It can only find patterns that are already there in the data. And this is true. But on the other hand, we have more advanced methods like unsupervised learning, where you can, for example, here find different kinds of patterns in one picture, like what is the content of the picture, and find other patterns like what is the color, what is the drawing of the picture, and then combine those pictures, and you will come up with very interesting results. This is something, by the way, I really love to do. I'm creating a lot of art with artificial intelligence, and it's a way to get into a new creative process. But in the end, we are still at a point where AI is not creative by itself. So it's not inventing something new, but you can find more than just routines. And the big issue is these deep learning algorithms are black box algorithms. Some people say, especially in the field ethics of AI, an algorithm has to be explainable. This is bullshit, I think, because if you could not explain an algorithm, you could not program it. Or the other way around, if you see the programming of an algorithm, you have the complete explanation. It's just mathematics. But just think about, you have a mathematical equation with 1 trillion parameters in it. You don't know what effect on the results which parameter has. And this is why these algorithms really are black boxes. And we don't know what kind of patterns they learn. And it's very difficult to find out why these algorithms work. And some techniques are developed there as well. So what you see here is this picture was created with an algorithm that is trained on YouTube videos. And then you enter a feedback loop so that the algorithm is altering the picture in a way that it looks more like what the algorithm would love to find in the picture. And so in the end, you see, if you train an algorithm on YouTube, you probably in the end come up with a lot of dogs and cats, because this is the content that you find on YouTube. Finally, what are now the challenges? And let me connect this to political science. We have some general and ethical challenges. It's the question of data access, who has the data, and this is a political question, because it's quite clear that the rising of Google, Facebook, and Baidu, for example, as the most important AI companies, has a lot to do with the access of data that they have. And you might know that um, data access is a political issue when it comes to privacy. There are very different privacy concepts when you compare, for example, China with the US or the US with Germany. And there you see all these questions are really important and rooted into a political setting. But it's not only data access, it's the quality of data as well, and the actuality of data. Nothing is as boring as data from yesterday. You always want to have the freshest and nicest data to build your models. Then we have some general bounds of pattern recognition. So as long as you're doing pattern recognition, the computer can only learn things that are already given in the data. But if you have a process that is totally new, something really new happens, like let's take this COVID pandemic right now. Many things are changing, and many data sets that you have are broken. They won't work anymore. So if you have now any kind of AI model that is based on pattern recognition, you might run into problems. And reproducibility is the next big issue. So the models are getting bigger and bigger and bigger, and it's very expensive to retrain a model just to see if it really works. So we are now, even in computational social science, we are reaching a point that is quite familiar from physics, where experiments are uh, so expensive that they are normally not reproduced. And this leads to a very different, difficult situation for the progress of science as a whole. So, because normally you would say results should be reproducible and be reproduced to see what happens. Um, One word to accountability, because this is important as well. The more complex these models become, the more difficult it is to hold anyone accountable for this. So let's say you are using an AI algorithm in medical environment, and this AI algorithm is built on a model that was built on YouTube videos, and now you retrained this data, and someone else developed this, someone else developed the algorithm, you are using it just now in a hospital or whatever. Who is responsible for mistakes that are made? This is a very difficult question, and there is no one answer to this, but you see there is a whole cosmos of political question that really comes from the technical perspective of these algorithms. And for political science, in more precisely, I think on the one hand there is a huge market now for political scientists that are able to understand these algorithms, because in every company, in every government, someone has to answer these questions, and um, you should not let the engineers do this, because engineers always think that uh, uh, for every problem there should be a technical solution. But for many problems, there is no technical solution because they are not technical problems. Take, for example, hunger in the world as a huge problem, but it's not a technical problem. It's not the problem that there is not enough food in the world, and that we need a better production of food and any technical solution. But the problem is uh, we are talking about power structures. We are talking about policies and politics that don't fit. So there will never be a technical solution. But if you want to be able to discuss these things and discuss what AI could do to help something, you really have to learn something about these algorithms. Um, Big issue there is a bias in machine learning, and this is connected to all the black box arguments. It's very difficult to find out what these models are really doing, but the more machine learning is integrated into our daily life, for example, facial recognition, um, the more politically it becomes, and the more important it is that standards that are not from from a technical perspective standards, but from a political perspective, like equality, equal access, all these are somehow integrated into these models. And this is why I always like to say, in the end, the mind is free, the model is not free. So the model is always designed by the ideas that some engineers already had in their minds. So the model is not finding anything new. The model is just trying to solve a problem that might not be a real problem in the end. So it's very important uh, to think about the limits of machine learning, and to see where we can go beyond machine learning with creativity and with a political attitude, and to see what is really happening in the world around. But this world around is already changing, and it will change in the coming years a lot, and we will see an even faster rise of AI. I'm very sure about this. So this was it from my side, and now I'm very interested in your questions and would love to start a discussion with you.